And
Hi, everybody.
All right.
Okay. So I'm going to quickly go through the stuff I went through before, mostly because I don't have a recording yet of it. I'm going to have to make one. So when I do, it'll be uploaded. But just very briefly, because you're going over the homework. We talked about last time. We talked about electric charges. Idea is that once you get down to the atomic level, particles have a property that causes them to attract or repel each other. And so we define that as electric charge. We define the value of the electric charge as this. Each particle is going to have that size charge. Whereas what we're defining is 1 coulomb is some bread box amount, something you can, something on the size of a kilogram or a meter is something we can deal with in the real world. So, there's lots and lots and lots and lots of, say, electrons in a coulomb. And we're also talking about the masses of the atomic particles. And so the story is going to go here is that when we talk about large objects that have electric charge, it's going to be that they have either an excess or a deficiency in the number of electrons they have. Positive charge things will have fewer electrons than they need, and negatively charged things will have an excess. That positive and negative relationship, I didn't tell you about this. That came basically when we were first studying Ben Franklin, the whole kite and key and the thunderstorm thing. Basically, they had to pick what they thought electricity would do. And they thought that electricity would be positively charged particles flowing from one place to another. And then when we actually go and measure it, we find out that it's not. It's flowing the other way. It's negatively charged particles. So it's just we assign labels and we assign them wrong. There's a point with it. Right, so this part is quantization. Is that whatever charge we measure on a macroscopic object, it has to be an integer number of electrons. All right, so that'll help you when you calculate stuff. You're not going to get some half an electron extra. Not that that actually matters very much, because anything you can measure is going to be an insane number of electrons, and that half an electron would be somewhere in the rounding area. All right, so, but a coulomb is about, not quite, 10 to the 19 electrons. We talked a little bit about picking up charges, and in that class, which is a week ago now, we did the playing with pieces of tape that have picked up electric charge. But the traditional way of talking about it is the things that people would have had access to, basically hard rubber, glass, animal fur, silk, cotton, felt, that sort of stuff. Things where you can cause it to easily transfer charge from one thing to another. And the gist of it is what we deduce is that if you get a charge from somewhere, if you get a charge on an object, it has to come from somewhere. So net electric charge is conserved. And we talk about like charges repelling and unlike charges attracting, and uses of that. We talk about conductors and insulators. Things that allow charge to flow easily are conductors. Things that hold the charge and don't allow it to flow easily are insulators. In general, as sort of a stereotype, good heat conductors are also good electricity conductors, and vice versa. Though you can find objects that are good at one and not the other. All right, so we talked about how do we spread charge. So, by the way, this last lecture I would have done on the chalkboard because we didn't, we had a power outage, slides wouldn't come up. So, not the slides, the TVs in the room. So, you have an object you want to accept charge. If it's a conductor, one way to get it to take charge is by contact. You put an object against it, since it's free for electrons to flow, then the electrons flow onto it and give it a charge. Another way to get charge to show up is by induction, which is you bring the charged object near, and it will have, say, an excess of electrons. It'll be negatively charged. It will push electrons away, which leaves one side of it with a positive charge, as you see here, and the other side with a negative charge. Now, if you give those negative charges somewhere to go by connecting a grounding wire, then they'll follow it and go further away. And that gives you what's left over is a lack of charge. You push the charges away without actually touching one object to another. So in the homework, there will be questions where you start with an object and some other objects that aren't charged, and you manipulate them in certain ways and try to reason out what happens. Right? And the general rule is if you're working with conductors, the charges want to spread out equally amongst them. All right, so you can do things, I talked about this is what we call polarization. Is in insulators, you don't have charges move a lot, but you have them move on the atomic level. They kind of just stretch out a little bit. And basically the atoms don't give up electrons easily, but you'll still get an effect of a slight overall charge on one side and the opposite effect on the other side. And that's going to be an important mechanism is when we talk about storing electric charge. When we put electric charge on an object, it's going to generate electric fields. If you insert an insulator, you can lower the amount of electric field. Effectively, this thing, the rod here, is going to have negative field that way. But the material is going positive and negative. It's going to have electric field that way. And it's going to decrease the total field. Now in the lab, y'all should have explored electric field a bit. And we're getting into calculating the forces and then calculating the fields from charges. So, yeah, so we had unlike charges are going to attract, and so and the table just moved. That's weird. So when they attract, they're going to pull towards each other. You can label these F12, F21. Actually, I should probably flip that. That's but when you do that, you realize that those are third law forces. And the same thing goes here. This is F by 2 on 1, F12. And this is the repelling case. All right, so for that, we have what's called Coulomb's law, which lets you calculate the size of those third law forces. It doesn't tell you the direction, it just tells you the magnitude, it just tells you the size of it. All right, and that's why there's these absolute value signs in the formula here. And we define what K is as a constant. The reason we do that is because in the lab, we work with things that we can tangibly hold: kilograms, meters, coulombs. And so we need something that converts the units appropriately. And so this secondary constant here will come up later. It is more of a constant, more of a universal constant. The idea is we talked about insulators, how they polarize. That gives a constant epsilon that is different from this one. This epsilon naught says, what if I don't have a plastic there in the first place? It'll make sense when we get to it shortly here. But that is, we're talking about assemblages of charges and how the field relates to the charge setup. Anyway, so we have a formula for the force based on the distance between the charges and the size of each charge. And from that, you can see if you increase one charge, you increase the forces between them. If you increase the distance between them, you decrease forces. And so this is where we get into actually calculating stuff. This is where we get into how do we reason about problems and calculate about it. And that was the goal for today, was to actually do calculations on things. And we'll deal with some fairly larger numbers. All right, so we'll have a charge of half a coulomb and minus 3 coulombs, and they're 3 meters apart. And we want to find the force one charge puts on the other. And then since we found a force, we would like to use the mass of that object and find its acceleration. We'd like to use Newton's second law. In general, we're still doing the same sort of stuff we did in first semester. Is we want to describe the motion of objects. If I take, if I take an object like a piece of tape in the previous demo, and say it's 5 grams, and I'm moving it around, I'd like to know what the forces are on it. So, when you're doing problems like this, you should draw a picture. Let's draw a picture. There's one charge. I'm going to label it positive. That's going to be the positive charge here. This is going to be the negative charge. And so the distance between these is 3 meters. And so this is, the right side is the minus 3 coulombs, and this side is the plus 5 coulombs. And so this seems like a very simple thing. One equation, plug and chug, and it is. But you want to reason what directions the forces are going to act on as well. That might be important. So we're going to draw in. They're unlike charges, so they attract. And that means the positive charge goes towards the negative one. And then the negative charge goes towards the positive one. So those are our forces. And then we just go calculate. So I'll often do K is 9 times 10 to the 9. Newton meter squared per coulomb squared. The slide said 8.99, and I'm sure your textbook says that. But it is, rounded up to 9. Especially since we're dealing with one sig figure. So So 9 times 10 to the 9 Newton meter squared per coulomb squared. Now, these are absolute values. So we're going to have 3 coulombs and 0.5 is not 8, that is 5 coulombs. And then 3 meters squared. So when we look at that, we have 3 meters quantity squared. That's going to be 9 meters squared. So that meter and those meters cancel out. I should do this in a different color. Cancel the units. These coulombs and this coulomb and that coulomb cancel. So we'll have newtons. That makes sense. And then we do the math. This 9 and that 3 squared cancel. So we'll have 1.5 times 10 to the 9 newtons. So that's going to be our force. I'll give you all a moment to write that if you're writing it down. Did people get that, or does that make sense to people as they're doing it? You had problems in the lab calculating this stuff. I think most people that turned it in on Tuesday, they got it right, and I don't see any issues with it. Again, I was looking at it there, not sitting down and actually calculating that stuff out. So clean slide. F is 1.5 times 10 to the 9 newtons. And going back to this, we only drew in, effectively what we drew here in this picture is the free body diagram. There's only the one force on it. All right? We ignore gravity because gravity is super weak. And we didn't identify anything else, like friction. You know, we just said, here's an object somewhere in the universe and it feels its force from another one. So we're just going to do net force is mass times acceleration. And our mass was 5 grams is 0.005 kilograms. And so our acceleration is force over mass. There's our force. There's our mass. And in here, this newtons, the definition of that is kilogram meter per second squared. So you'll have an acceleration, that makes sense. And 1.5 times 10 to the 9 divided by 0.005 is 3 times 10 to the 11 meters per second squared. And that is kind of ludicrous, because ballpark, what that means is you would reach the speed of light in about 2 milliseconds. All right, because this is basically velocity is acceleration times time, or average velocity. You're starting from 0, getting up to the speed of light. And so, yeah, you're going to about a couple milliseconds. So, just because electric forces are fast, and you will get like big numbers. And so in general, we don't deal with coulombs, we deal with smaller units that will generate smaller forces. We'll go through some other examples. These are also further in the slides. I've mentioned in the previous class, our model, our original sort of thinking of the atom, because the force depended on 1/r², that looked like gravity. And so we made models that looked like gravity. And so we imagined electrons moving around the nucleus of an atom like a planet going around the sun. Now, of course, if you take chemistry, you learn that's not true at all. Eventually, you learn that. But by making this model that's not right, because you can still find interesting stuff, and we're going to find the speed of the electron in hydrogen, assuming that it moves in a circle. So we have a formula for the force. But if we have something moving in a circle, we have circular motion. And we can also write that the force looks like the mass times acceleration. So that's going to be our attack, is we're going to set these things equal and use that to figure out the velocity. And if you do that, you'll get, let's just go to the next slide. Yeah, so you'll have mv squared over r is k q1 q2 over r squared. This r and one of those cancel. V is going to be k q1 q2 over mr. You take a square root, and then you put the numbers in, and that's what's going to happen in the next slide. Is effectively we're going to calculate the force instead of calculating directly. Then calculate the velocity. That's what happens here. We calculate the force. The force between the proton and electron is quite small because we're just putting in, right, the square here is both charges, and the distance between them. And we get a very small force. But that very small force is causing the charge to move over a very small rate, a very small circle. All right, so we put that in. And what we get is that the electron is moving something like 2 times 10 to the 6 meters per second. So as a complete aside, why is gold the element? So what's happening in elements is, as you increase the mass of the element, all right, if we went to helium, then this charge that's in here would go up. Instead of being a nucleus with a charge of 1, it'd go to charge 2. When you go to gold, it would have a charge of 79. Right? It'd be, the nucleus would be like 79 electrons, and the single electron we're looking at would have 1. So each element would have roughly an increase in force. The other thing you have is that the radius changes. All right, so each atom gets bigger or smaller, but they get bigger or smaller based on their electric charge, how they fill the energy levels each shell, and how the electrons actually orbit. So for when you get up to about gold, if you did this calculation, you'd get a number that's too big. It'd be larger than the speed of light, which means that you have to correct for that. You have to say that there's a relativistic correction. And what that does is it changes the properties of the atom that you would expect to what they actually are. And one of the ways it does that is it changes its color. It makes it gold instead of silver. Most metals are silvery. Anyway, that's a complete aside, but the point is you can do this sort of calculation and get useful information out of it. All right. Other example things. Eventually, the point of this class is to get into calculating vector math. So we have three charges on a line, and we'd like to find the force on Q1. So this is the one we want. And looking at the charges, we have a minus here, and a plus here, and a minus here. So Q2 and Q3 are going to attract Q1, and what we get is pull in different directions. And that's the picture we have down here. This is our free body diagram. And what it's going to tell us is if we calculate the pull from each charge, we're going to end up having to subtract. Right? So we can do that. We can calculate what F12 is. This is another thing. This is where we start using realistic units. 1 microcoulomb is 10 to the minus 6 coulombs. 1 nanocoulomb is 10 to the minus 9 coulombs. Right. If you remember SI prefixes, the things I know they tell you in elementary school for a test. I know that it comes up in chemistry and it comes up in physics, but this is generally where it comes up because electric charges are so much generally smaller than the playground size forces, the lab size forces, or units that we're expecting. So for one of these, we plug and chug. And we have our distances here. So this is going to be. And we do a bunch of calculation. And what I get is 2.7 newtons. Does other people get that, or does that make sense? Once you get to here, you're kind of just multiplying. All right, we have 10 to the 10 times 10 to the minus 6 is about 10 to the 4 times 10 to the minus 6 is about 10 to the minus 2 divided by 10 to the minus 1 squared. That should be about 1. So our number makes sense. Now, of course, what we have to do is also calculate F23, K, Q2, sorry, Q1, F13, Q1, Q3 over R. And here's where I want to put in, you can put in notation where the radius is, right? This is R12, this is R13. So I left that in so that we already calculated. What we notice is the radius is a little smaller and the charge is a little bigger, so we get a larger force. All right. And then finally, we go back to our free body diagram and we realize that this is 2.7 newtons and this is 8.4 newtons, and they're in opposite directions. So take this way is positive, and this is negative. And that's where we get this here. So this is kind of leading us into calculating with vectors eventually. So anyone have any questions thus far? So, went 30 minutes without asking that. Everyone's okay, I guess. Okay. All right. We introduced this idea of the electric field in the lab. I'm just going to go over it briefly. The idea is we might have, like, let's say we want to move something around with electric forces. So what we would do is we'd set up in the lab, we set up some conditions where if we have a charged object, it will feel a force. And what we'd like to know is what conditions do we need to set up? So the idea is we have this thing called a test charge. It's a very small charge that will feel forces. It'll test what is going on amongst all the other things. And so what we're doing is we're isolating. All right, if we have this formula, right, for the force. What we want to do is isolate the thing in parentheses is the environment. And then this will be Q naught. This is the test charge. We're going to isolate the thing that feels the force from the environment and say, what does the environment do to cause the force on the thing that feels it? So when we say test charge, this is that it feels the force. But it doesn't cause anything to change the environment. So when we do that, the thing in parentheses is what we're going to call the electric field. But first, we have a practice problem. We set up some environment. Right, it feels this force. This is F, and the test charge has this value, so this small value, 30 nanocoulombs. Now it is to find the force per coulomb. This is what the electric field is ultimately. And then the goal is to use that to predict what happens if we quadruple the test charge. And if you do that, if you quadruple it, if you go from 3 to 12, it's going to increase the force by a factor of 4. Right, so that would tell you, hey, this force goes from 6 to 24 times 10 to the minus 8 newtons. Force per coulomb is F divided by Q naught. And we do that, you get 2 newtons per coulomb. So this thing is the electric field, and the units are going to be newtons per coulomb. And then we can use that to calculate. The idea is that this thing in parentheses here is our KQ1 over R squared, and this is Q naught. Right, so in a way, we're still doing Coulomb's law, but now we've isolated it out. We have the thing in the environment and the thing that feels the force. And so this gets us to the definition of the electric field. This is what we're defining. And then also defining our units. You'll also see this as F is QE. And generally that's the more useful version of it, because what you're going to do is talk about the electric field. And the idea is that you can measure the electric field with a test charge. And so you don't know, or you don't have to know where all the charges are in the universe. You just have to know the field that you've measured with a test charge, and then you can take that and use it to calculate forces on other objects with charge. The idea is that we're isolating things to make it a little easier to calculate stuff. Right. So what I want to point out of this is the electric field is pretty much constant. It's based on the arrangement of charges in the environment. Right? So in this picture, we have positive and negative charges in these objects. And we have a test charge, which is Q naught. If it's positive, then it feels a force in the direction of the field. If it's negative, it feels a force in the opposite direction. And that kind of makes sense. Is we have basically positive charges below the thing, below the test charge, and negative charges above. So the positive charge will be attracted to the negative charges, and that's why it goes up and to the left. And then the negative charge will be repelled by them and attracted to the positive, and so it goes down to the left. All right, so this is the force you calculate has some direction, and it isn't necessarily the direction of the field. So it's usually along the direction. It's either same direction or opposite direction, because it's just positive or negative that shows up. So the idea is that can we calculate, given a particular magnitude of the field, this is E, and these are our Q's, can we calculate the force? And that's fairly easy. We're just going to do F is QE. And the key thing is we're going to keep the signs in. There's no absolute value symbols. So what we're saying is that this direction is positive, and so this direction is negative. But then we're just going to take these numbers, plug and chug. We'll have Q is 18 times 10 to the minus 8 coulombs, and E is 2 newtons per coulomb. And so we get forces from it. Now they put the, in the slides, there's absolute values because we're just telling the magnitude. But the directions here are in opposite directions. Okay. I'll pause for a second. Questions? Everyone's okay? The light is coming directly over two students, so I can't actually see what's going on. But everyone's okay so far. Okay. All right. Again, another example. We have a point charge here. So these three charges are 15 microcoulombs. And then we're putting a test charge. R is 0.20 meters. And it can have a test of 15 microcoulombs. And that is that we want to find the electric field. Well, we don't need the extra test charge. I mean, you can do that if you want, but we don't need it. Right? You can just go and realize that this is K Q1 Q0 over R squared divided by Q0. All right. So the point of this is that the electric field is going to be KQ over R squared for a single point charge. Well, if we go the long way around to do it, we calculate forces and we get a force out of it, and we go and we're basically, we're dividing by these numbers here. So another reason I'm showing you this is that I want to show you the scale of reasonable numbers, right? To get like 1 to 10 newtons, you're going to use microcoulombs of charge and fractions of a meter in distance. And that's going to give you electric fields that are large, like on the order of millions of newton per coulomb. The point of this, though, is that we have a formula for the electric field that's independent of how we're going to test it. If we know how the environment is assembled, how the charges in a particular problem are set up, we don't need to introduce a test charge. We can just calculate the electric field. And so we have a formula for it. And again, this is the magnitude. You have to consider the directions. And the directions are based on what you did in the lab, how the field lines go from positive charges to negative charges. Right. So here we have a problem. We have positive charges. One is 16 microcoulombs and the other is 4. They're both positive, which means each one is going to generate an electric field away from it. Now, the distance between these is 3 meters. And we want to find a spot where the electric field total is 0. So what we want to find is that E1 plus E2 as vectors is 0. For that to be true, they need to be in opposite directions and the same size. So E1 is E2. So that's what we're looking for. Well, we can take this formula and actually write what that looks like. We'll have K Q1 over D squared is K Q2. And now this distance here is 3 meters minus D. So we'll have 3 meters minus D squared. And that's what happens. You can put numbers in if you want, but what we end up with is our unknown is D squared here. That can make the problem a little weird, so I'll just go ahead and jump to the answer. And it's that the K's are all going to cancel out. And the 10 to the minus 6 coulombs will cancel out. And so effectively you got 4 times this thing on the bottom on the right equals the thing on the bottom on the left. And so that you get the D is 2 meters and then the other side is 1 meter. So if you remember in the lab, we had a problem like that at the very end of it. We had an arrangement of charge that included 2 positive charges right next to each other of different sizes. And the question was there a spot where the net field was 0? And you could see it in the field lines that there was a spot with no field lines in it. And that was it was between the 2 charges and closer to the weaker one. All right. So this is where we want to set up problems that we're talking about adding up vectors and such. And you can do this for forces as well as fields. But in general, when we're talking about calculating forces and fields, they can be in arbitrary directions. And so we have to accommodate that. We have to find the vector directions for everything. So the goal of this is to talk about calculating components for things. Right? If you remember when we did all the way back, first week of 111, first couple of weeks, we calculated vectors, and then we calculated vectors for motion, for kinematics. And then we did free body diagrams and all sorts of calculating vectors there. And so you have to remember is that between these charges, so here's a positive charge and a negative charge. We're finding the force on this charge. It's going to be along this line. It's got components Fx and Fy. And that is effectively what's in the picture here. All right, so when we find that, and we find this free body diagram, what we're going to have is the net force looks like F13 and F sub x, and then F sub y. And that's going to give us the total force. All right, so it's going to be like we did in 111, is that you have to, when you add two vectors, you have to break it into components, add the components up, and then assemble your sums of components back into a vector. For those of you that had the other professors, how did they explain that to you? Was it like kind of like what I said, or was it okay? Good. I always have like one or two students that try to do like they just learn about trig identities and they try to use those. And I don't want them to do that. I just want them to do this breakdown and reassemble, like I said. Let's say we wanted to do this. We wanted to actually find this force. I should have had a slide here for this. All right, so we're going to draw pictures 4, -5, -6, I believe. Yeah. 0.1 meters, 0.15 meters. So, and then we want to label these 1, 2, and 3. Yeah, that's the way we want it. And we also want this angle here. All right, so the point of this is that we want to find F12. Well, that's going to be in components. It's going to have, first find the magnitude of it, right? Find the number. This is going to be K Q1 Q2 over R squared. Then we find the X component is F12 cosine 73 degrees. F12 Y is F12 sine 73 degrees. And then we would find F13 is K Q1 Q3 over R13 squared. All right, so this is 0.1 meters. This is the 0.15 meters. But this has the X component is just, all right, we'll have cosine of 0. And F13 Y is F13 times 0. That's 0. And that's just showing what we had before is you're just adding the components up. So we would have the net force has an X component that is, I'm running out of slides. Anyway, we would add up the X parts and we'd add up the Y parts. And then we would use our trig functions to go back. Yeah, our Pythagorean theorem, inverse tangent, to get a new angle and a new. This is I need to put. All right, so we have what we've calculated. And so now we'll do, nope, give me the pen back. So now we'll have Fx as F12 cosine. And Fy is F12. All right, so that would be our components. And then you want to do magnitude and direction, size of f, square root fx squared plus fy squared. And then inverse tangent of y over x is triangle theta. All right, so I want to have that in the notes in case you're going to read over again. There's a process to that. And notice I haven't calculated anything. This is a generic sort of, you would find the x parts and the y parts and then plug back in. All right, this is. So when you're doing these problems, I do want to comment that you can recognize sometimes that there's going to be symmetry involved. All right, that we have a set of geometries here where you note that there's different charges here. Here, this charge is negative, this charge is positive. Here, these charges are both negative, and then these charges are both positive. All right. So you can notice some symmetries here. And what I want to do is draw in a different color here. Right, in the top picture, right? What we notice is that this charge and this charge are the same. If we put in arrows here, the electric fields at those points, right? This is E1 and this is E3. Those electric fields are the same size because they're going from the center to the corners of a rectangle. And they're in opposite directions. So they cancel out. They just go away. And so if you see a problem where you have 4 charges, but you realize those two, they cancel out anyway. You don't have to calculate them. You would have to calculate 4, which is going to be inwards, and 2, which is going to be outwards like that. This other problem, there's a symmetry in this too, is that you can divide it directly down the middle. The left side looks like the right side. And so what that means is you're going to have different pairs of forces going on. Like if I took a look at these two electric fields, where I'm pairing up 1 and 3 and 2 and 4, they're going to have components. And the x components cancel out and the y components don't. All right, so you can see some symmetry there that will help you simplify problems. This goes on in other places. You can find other techniques to solve problems like that. Like if you see a ring of charge, say you have a circle and you have 4 positive charges. You want to know what's going on in the middle. You can realize if it's symmetric like that and they're equally charged, then there's going to be no effect. Now, if you take one of them away, it's like replacing it. It's like adding a negative charge there. Right? You have a positive charge and you add a negative charge to get rid of it. So the net effect is going to be like, well, just have a negative charge and none of the positives. I should probably draw that out. That's okay. All right, I got about 20 minutes. I want to keep going as much as I can because I would like to get through everything you need and then not have class on Thursday. Just do the exam on Thursday. That's what I want. Now, in the lab that you saw, I mentioned the idea of a capacitor. The idea is that we had assemblages of charge. Right? In this case, you looked at lines of charge, 2 lines going across the screen. And you had positive charges and you had negative charges. And this is a special case where we're telling you what the electric field in this situation looks like. It's going from positive to negative, essentially straight down here. And then the positive charges will go upwards, and the negative charges will also go upwards. And it has a size. And notice that we're bringing in this epsilon naught again. All right. Charge density here is Greek letter sigma is Q over A. Now, there's some stuff we don't cover in this class that we used to cover that actually shows how you do this. And it's effectively what we're doing is we're counting the number of field lines that go through a certain area. And we're using that to deduce the charge it has to create. And that's I'll bring that up in another class, but effectively it's what you did in the lab is you saw the number of field lines that you had corresponded to the size of the charge. Right, that was that one section on the other website. So we have a formula for calculating the electric field. Now, we're going to come back to this because capacitors are things we actually use. They're in electronic devices. They store charge or they store energy. And the way they do that is these charges are attracting each other. And if we give them a way to connect, the electrons will go from one plate to the other. They can't do it directly, they have to go through a circuit. All right, so going over what you should have seen in the lab, electric field lines are lines that indicate the direction positive charges would flow. They map the electric field. And they have some conditions, right? The idea is you would probe around a charge and you would see which way, with our test charge, which way the force would go, and use that to map out what the electric fields look like. Electric fields always go away from positive charges, which we see here, and toward negative charges. If they start on a charge, they start on a positive charge. If they end on a charge, they end on a negative charge. They can go away to infinity. Right? Is that if this was the only charge in the universe, electric field lines would come in from infinity. They don't just stop, they keep going. So for a capacitor, we'd have a bunch of charges, bunch of positive charges, and the field lines would mostly go directly positive to negative. At edges, they would bend outwards a bit. And then you would have charges going, field lines going away in the up, toward the negative charges and away from the positive ones. They don't stop in space. They can go from infinity, but otherwise they don't just terminate. We talked about the number of lines is proportional to the size of the charge. There's some other stuff you can see that the field lines go positive and negative. Note that the field lines never cross. There's always if you draw a line, you never draw another line crossing. And there's a reason for that. All right, here you see two positive charges, and in the middle here, the electric field is zero. All right, and that's because if I wanted to know the electric field here, well, there's a component that way and a component that way, and they cancel. Okay. So, testing our ideas on that. There's things wrong with part A here. We can look at them. So one thing we might look at is the number of field lines, right? There is 8 of them on the positive charge of the 4Q. There's 4 of them on the minus 2Q, and there's 2 of them on each of the minus Q's. So that's okay. Let's see. We can look at I'm trying to find what the other ones are, and I don't see them. There is one obvious one at point P. Remember, I said field lines never cross. This is where I'm going to show what it means. So the field lines are supposed to indicate the direction a test charge would move. All right, so if I draw in effectively right and left field line, you know, they're going to the right or going to the left. And I'll put a positive charge here. Which way does it move? All right, the positive charge is supposed to flow along the field lines, and there it has a choice. And actual charged particles don't have choices. This is not allowed. What we would instead see is something more like that, where the lines avoid each other. All right. All right, does anyone have any questions thus far? Does that make does that concept of field lines and using them make sense? All right. So we want to talk about conductors for a bit. Conductors really like, charges are really free to move in conductors. So if we have an assemblage of charge, like in picture A here, they're all together. All those charges are repelling. They all feel a force pushing them outwards, and they're allowed to push outwards, and so they do. And so picture A turns into picture B. All the charges go to the surface. What that means is inside, there cannot be any charge in the middle of the conductor. And the charge creates the electric field. So effectively what happens is there's never an electric field inside a conducting material. It's always starting at the surface and going outwards. Actually, the arrows under here should be the other way around. And so what's happening is, let's say you had 2 negative charges there. Which way is the field going to go at the center? Well, one line will go that way, one line will go that way, and they cancel out. And that's effectively true anywhere in the conductor. If there was an electric field, then the charges would feel a force and they would move. Basically, in the conductor, the charges are always going to move until there is no electric field. They're going to cancel out any electric field that shows up. And so this is why a lot of electrical equipment has metal wrapped around it. The point is to keep the electric field inside or outside of the box, to shield it. So you can have, as long as you don't have charge in a cavity in the conductor, there's no electric field in it. The other thing we note is that the electric field will always be perpendicular to the surface. If it's not, then that means that it feels a force parallel to the surface, so it's free to move parallel to the surface, and it does. So it's always going to be perpendicular. Now, you can have charge inside a cavity And if you do that, this is what happens. You draw all the charges in the conductor are free to move. It was neutral to begin with, but they're free to move, so the electrons are attracted inwards. And they leave positive charges on the outside. And so the point is that conductors hide information about what's going on inside them. Is that if you see an electric field from a conductor, it tells you that there is charge on it or within it, but it doesn't tell you the shape of the charge that's in there. It just tells you the amount. And that's where, we're going to stop stuff that you need for right now, but I am going to go briefly over the other stuff, the stuff that we don't cover. The idea of this is we have field lines. We can find a way of counting the number of field lines, right? Or at least the density of the field lines. We can say, how many field lines pug through a particular area? Well, all right, and you'll note when we write the electric field from a point charge, the area here is 4 pi r squared. So it looks like we can find the electric field through a particular area. And that's what we call the electric flux. All right. Now, the point of this is that the electric flux is a property of the charge, right? The flux is just charge divided by a constant. And there's a reason for that, is that if I draw a charge, and we have field lines going out from it. Say we have 8 field lines going out from it. Those field lines don't stop in midair, they keep going. So here's one we have drawn here. If I draw a surface there and calculate the flux, it's some number. If I draw it further out, it's the same number. Right. I've increased the area and decreased the electric field in the same proportions. For arbitrary shapes, you just care about the field that's perpendicular to the surface. And so the point of it is that there's a law for figuring out the electric field based on an arbitrary distribution. And that's kind of the thing is, that's where we're going to stop for today, because it gets into heavier math I don't want to deal with. But the gist of it is, we figured out how to calculate forces and fields, and then a lot of other stuff in electricity is trying to find easier ways to do those calculations. All right, we're trying to avoid vectors in a sense, because vectors are hard when you're dealing with, when we talk about a charge distribution, it might be 10 to the 23 particles. It might be a mole of stuff. So we want to avoid trying to deal with vectors if we can avoid it. There are ways that we're going to skip over unless we do it next week sometime. But the thing I do want to take out of this is anything that's spherical, the electric field looks like a point charge. That's kind of an important thing to take away. Any spherical distribution looks like a point charge. Because all you got to do is go far enough away from it, and it looks like a point charge from far away. So that's where we're going to stop there. We're not going to do any more with the slides. Do y'all have any questions before I let y'all go? If you have homework questions, I have a meeting at 5:30, but you guys can hang around for 20 minutes and ask questions. Otherwise, we're done with the class today. No class on Thursday, just the exam. The exam's at 7 o'clock at CFS M7. So if you have questions on the homework, please let me know. Otherwise, You know, or if you have questions on the exam, if you want to ask stuff about that, then feel free to email me, let me know, or stay around.
I've got one more question.
Okay.
Real quick. Before you answer, can I answer my lab?
Yes, just leave it up here with me and. Yeah, if you got your lab, I'll take it. Otherwise, you can go. All right, let's exit out of this stuff, stop the sharing. In the meeting.
I had 2 of them asked.
Oh dear, the chat did not do. Why did it do that? I hope, let's